Okay. Good morning, Jihad. How are you?
How are you, Doctor? I'm fine.
Yes, good. Thank you very much. Okay, right. So I think we have quite numbers now, so probably we can start. I hope you guys have downloaded the new notes for chapter 3, which is on the introduction of corrosion electrochemistry. But before we start our new chapter, I believe we can have a little bit of discussion, probably this related with your assignment, assignment 1. So I think Mahdi was discussing with me about question number 9 and 10 related on the transference number. So if you still remember, last Tuesday we have finished with chapter 2 on the junction potential and the calculation of transference number either by hit-off method and also moving ionic boundaries. All right. So probably, Mahdi, what you want to say something about this one?
Yeah, I want to say about the Q. You said if if the Q is not given in the question, you can use the rule below is multiply T time with currents.
Okay.
So in this question in the assignment, you didn't give also the currents or the time.
Understood. Okay. So if you refer back to question number 9, maybe I can.
10.
Oh, number 10.
Yes.
Number 10. Let me open the question. Not sure whether you guys have the question with you, but maybe I can share. Not this one. Okay, all right. Probably I can share the question for those who didn't have a question with them. And I forgot to say hi to Hamda. Hamda, how are you?
Oh, fine. Thank you, Doctor.
Okay. So far, I think I've met Mahdi and Hamda in physical because Hamda came to see me yesterday for the first time. Okay. Right. So this is actually the question, number 10. Calculate the transport number of H plus ion from the following data obtained by moving the ionic boundary methods. So given over here are the concentrations of HCl, and then you have the weight of a silver deposited in the colorimeter. Okay, you have a distance, you have S value, you have L value, and then you have a cross-sectional value, S, which is equal to 1.25 centimeters square, and then equivalent weight of silver, right? Not sure whether you see this one. Is this actually given in the question?
Yes, Doctor.
Yes, Doctor.
Q, if you notice there. Q is equals to mass loss over molecular mass multiplied with valency multiplied with F. Is this given in your question? Mahdi?
Yeah, yes, but when I calculate, I get so big number.
You got what?
The number is so high of value.
The value of Q.
Yeah.
High. Oh, okay. That's all right. No worries. So as I mentioned earlier that if the question didn't give you the current or the charge, Q is actually the charge. So Q is actually equals to IT, okay? And if the current and the time are not given, if you still remember which chapter, we have a calculation, a Faraday's law. Using a Faraday's law, you can calculate charge by considering current and time. So if the current and time is not included, you can actually find or expand it into this one. So I believe this been included. So you have a mass loss. So meaning that the mass loss over here will be the mass loss of the silver, deposited silver, 0.12. Okay, you divide with 108, and then you multiply with the valency. The valency, what will be the valency, Mahdi, over here?
The valency 1.
Yeah, valency should be equals to 1. And then, how about F?
F is Faraday number.
Yeah, but if you notice, if you put this in the formula, so remember that the formula for calculating the T plus is equals to S multiplied with L multiplied with F multiplied with C over Q.
1000. Yeah.
Okay.
So the mass loss here for AG or for the H?
For AG or for H? You mean what?
The mass loss. We should put the mass loss for the H or the AG.
AG. You put
AG.
the mass loss for AG, but the transport number, the T plus that you should get, it will be corresponds to the T plus of H plus, not AG plus.
Okay.
Okay. All right. So the reason why is because in this case, it means that you have the concentration over here, which use is HCl. Okay. So that is why later on you will, divide at 0.1 divide with 1000. So over there, later on you will have like T for H plus is equals to S. S is actually the cross-sectional 1.25 multiply with L. L will be like 7.5. Multiply with Faraday constant, multiply with concentration 0.1. So since both, like on the top you have Faraday constant, and then bottom also you have a Faraday constant, so you just cancel out that one, and then at the end you will have like T plus is equals to S multiplied with L multiplied with C over this one, mass loss over molecular mass multiplied with valency only, and multiply with 1000, because F and F on top have been cancelled off. So I think with that you can try to calculate and you can get. Right, Mahdi?
Yeah, right.
Okay. Any other question related on your assignment? Anyone? Or you already done with the question?
Doktor, boleh ulang balik tak yang tadi tu, yang TH plus sama dengan S and L and yang last tadi.
I think maybe I wrote it somewhere over here maybe. Okay, let me just write this so that you guys can follow. Okay, All right, so earlier on, I've told you that T plus is actually equals to S multiplied with L multiplied with C multiplied with F over Q, isn't it? Okay, so we have know that Q is equals to I multiplied with T, or if we expand this using Faraday's formula, Faraday's formula actually relates charge and current. So we can expand this, making that Q is equal to mass loss over molecular mass multiplied with valency multiplied with Faraday's constant. So if I substitute this into this, what you should get is that TH plus is equals to S multiplied with L multiplied with C multiplied with F over mass loss over molecular mass multiplied with valency multiplied with Faraday constant, cancel off, okay? Then at the end, you can substitute that value, okay? S multiplied with L multiplied with C over mass loss molecular mass times N, okay? And remember, for your concentration, this one is actually 0.1, right? 0.1 N. And when you actually substitute over here, then it can be like what? 1.25 multiplied with 7.5 multiplied with 0.1 over mass loss is 0. What? Mass loss is 0.12. Where? Got the question. What's the value, Mahdi? The mass loss? Maybe.
I'm not sure.
Okay, so 1000 is actually coming from this one, because you know that normality is actually equals to mole over volume, so 0.1 over 1000. Okay, so this one you will get. Once you get the answer, you can calculate T minus if the question asks for T minus, because you know that T plus T minus is equals to 1. And T minus is equals to 1 minus T plus. Okay, is it clear?
Yeah, it's clear now.
Okay. All right. So without further ado, I think I will start the new chapter. So basically, the new chapter is completely different from the first two chapters that we have started. Okay, the first two chapters is basically on physical electrochemistry, and today we are going to start with corrosion electrochemistry. So corrosion is basically the application of electrochemistry. Okay, and starting from this chapter, we are going to learn about the fundamentals of corrosion. Okay, the process related on electrochemistry, the kinetics behind it, and then the techniques for monitoring. So the outline for I think this three chapters, chapter 3, chapter 4, and chapter 5, as I mentioned, we're going to have introduction of corrosion electrochemistry, and then chapter 4, we are going to learn about corrosion electrochemical kinetics. You are going to learn about the principle of polarization, mixed potential, okay? Butler-Volmer equation, how to derive Tefel slopes and whatnot. And then finally, chapter 5, we are going to learn about electrochemical techniques for corrosion measurement. So basically, chapter 4 on kinetics, chapter 5 on the techniques, okay, and chapter 3 on the introduction. Chapter 3 and chapter 5 is one of the longest chapter. Probably we will spend like 1 or 2 weeks for chapter 3, and then maybe 1 week for chapter 4, and finally like chapter 5 we're going to spend like 3 to almost 5 to like 4 weeks, or maybe 2 to 3 weeks, right? So basically what you can understand about corrosion, anyone can give a simple definition of corrosion. Someone can try, maybe newcomers. Atira, you want to try? What does it mean by corrosion?
Corrosion is like a reaction between a material and its environment. Contoh macam pengaratan, corrosion berlaku on metal. Bila satu metal tu like besi or something terdedah kepada environment yang ada like rain or something acidic, ia akan buat permukaan metal tu jadi macam like appearance dia macam bertukar, like kehijauan or a brownish color.
Right. So forgot to tell you guys that Atira is actually Atira postgrad student or undergraduate student?
Saya postgrad.
Postgrad, master PhD?
Masters.
Masters, okay. Atira is actually a master student from University Malaysia Perlis. So she joined us to learn about corrosion. Okay, so welcome back to Atira. I think we have a few people who are taking masters in chemical instrumentation, taking this subject as part of their core subjects. All right. So what have been explained by Atira? Yes, it's true. But I think the most simplest way to define corrosion is basically the metal degradation. Okay, it's a metal degradation. The materials is actually degraded due to what? Due to the exposure to the environment. So the environment that we are talking about is with the presence of oxygen and also with the presence of water. So this is basically the concept of corrosion. Okay. Meanwhile, by actual definition, it is actually the chemical or electrochemical reaction between materials and its environment that produces a deterioration of material and its properties. Because you know, once this material has been exposed chemically or electrochemically to the environment, it will degrade, and later on it will change the properties of the metal or the materials, right? So as I said, corrosion is actually the degradation or the deterioration of materials, usually a metal, by chemical or electrochemical reaction with environment. Deterioration by purely physical causes is not corrosion, but described as erosion. So you know that the difference between corrosion and erosion. Corrosion is actually more on the chemical attack. Meanwhile, erosion is more on the physical attack. You have like water moving on and erode the surface. So this one we call it as erosion, not corrosion. But corrosion is basically resulted from the chemical reaction. All right. Corrosion is a natural occurring process. I will explain to you why, in which metals return to its stable state, the original ore. Okay. And corrosion is the extractive metallurgy in reverse. And another thing that you have to put in mind is that for corrosion, we have used one term, which is known as rust. Rust is actually a product resulted from corrosion process, and normally rust can be categorized only for iron. Okay? Or even though we have brass, zinc oxide, but rust, normally we use this term for iron. Okay, all right. So those who have learned about metallurgy, extractive metallurgy is the process where we can extract metals from the raw materials. You can actually produce pure metals by extracting the metals, the pure metals from the resources, which normally comes from ores or metal scrap. So the ore or metal scrap or metal oxide is normally exists in a stable condition because oxide has been formed, so it is no longer reactive. It's already thermodynamically stable. Okay. So when you do extractive metallurgy, okay, you do the extraction either by pyrometallurgy, hydrometallurgy, or electrometallurgy. So this is actually just an I think introduction for you guys who not sure about extractive metallurgy. So extractive metallurgy, we can categorize it into three parts. So we have like pyrometallurgy. Okay, we have hydrometallurgy and electrometallurgy. Okay, so pyrometallurgy, it means that the extraction of metals by means of heating. Okay, because you see over here the word pyro. Pyro means heat. Okay, and we have a few different techniques for pyrometallurgy depending on the types of ore that we are dealing with. We have calcination. Okay, we have roasting. We also have smelting, and etc. So the other one will be like a combination with electrometallurgy, like thermo-electrometallurgy. Okay, so calcination, it means that a direct heating of a material which actually converts or remove out the unwanted sources. Like for example, if you imagine you have like calcium carbonate. Okay, you have a calcium carbonate. Okay, so when you do a direct heating, what happens is that this will become CaO, calcium oxide, plus with CO2. Okay, so you can balance out the equation. 2 over here, 2, and you have 1, 2, 3, 4, like 2 over here. Okay, so the conversion of metal carbonates or what sort of metal oxide, metal carbonates, for example. Okay, we will do calcination. It's the direct heating process to produce calcium oxide. So there later on you can actually produce like a pure calcium or pure metals from smelting process. Roasting, meanwhile, is a process where you introduce gas. In this case, if you have like sulfide ores, example, like you have FeS, you have sulfides there. Okay. So when you react it, when you heat it with the presence of oxygen, what will happen is that it will become iron oxide plus with sulfur dioxide. Okay. Smelting, meanwhile, is a process where you melt, okay, the metal oxide into a pure metal. So in this case, from metal oxide, okay, when you do smelting, what happens is that it will form a pure Fe. Okay, right. So this is actually the pure metal that's being used for the production of materials. And you know that the pure metals, since it exists thermodynamically unstable, it tends to react back with oxygen to form a more stable product like metal oxide. So in this case, this process is known as corrosion. Metal extracted from their ores are high in energy states, thermodynamically, and not stable. It is this tendency of metal that recombine the elements present in this environment that lead to the phenomenon known as corrosion. I think the few examples of corrosion in man-made structures can be seen. Like for example, this one is actually a corrosion of reinforced steel in the concrete wall. You can also see a localized corrosion by formation of pittings in the structures like this. Okay, see the same thing. I think the corrosion in the pipelines. Okay, and others will be related on the corrosion in electronic devices. So have you ever experienced something like you are watching television and suddenly you want to change your channel, but when you press you notice that there's one button, maybe you want to press 1, 2, 3, channel 1, 2, 3. So when you press 1, 2, 3, number 2 is not functioning. You try to press it hard, even it's not appearing. So Did anyone knows what's the reason? Yeah, do you have any idea on this? Jihad? No?
الدكتور. Hello.
You have any idea on this? Not really.
Yeah, that's corrosion.
Basically, if you notice inside your remote control, you will have like a circuit board like this. This is actually where the button will be functioned. So most of the, I think, a spoiled remote controls normally means that you will have like the corrosion that happens on the contact. Okay, probably you might wonder, how does this corrosion happen? Maybe you are when you press the remote control, your hand or the remote is quite wet.
Can we name that electrical corrosion?
Yeah, this actually, this type of corrosion happens in electronic devices, and yeah, like that's part of the example that you can see. So when you have a corrosion on the contact, so that is why you'll see that when you press the button, it's not going to function because it's already become resistant. Okay, it's already forming like metal oxide, so it's quite resistive. Then it cannot like give a good connection or conductivity. Okay.
Okay.
So the cost of corrosion worldwide is quite high. Like it has been estimated that around 4.2 or almost 5% of GNP. GNP stands for gross national production. Okay, we also have GDP, which is a gross domestic production. Right. The cost of every country's GNP or GDP is due to the replacement of corroded components. Of course, you know that in every structures, when it has been like corroded, when you have a damage, you need to do maintenance or you need to do servicing. So most of the costs have been like allocated there. Cost of maintenance, servicing, cost of rebuilding and construction, equipment capital, use of resistant alloys, use of coatings or inhibitor, electrochemical protection measures, chemical expenses, environmental regulation, and safety consideration are all actually allocated under the direct cost. Meanwhile, for the indirect cost, you can also have like a production during downtime. Downtime, it means that during the production of a product, for example, like in oil and gas, when you have a leakage, then you have to shut down, okay, the operation. So the shutdown of operation is known as downtime. Okay, then you will have a loss of product due to the leakage. Of course, as I said, if you have a corrosion in pipelines, if you have corrosion in like vessel or tubes, it can cause leakage. And when you have a leakage, then of course this will be dangerous. Okay, because it can create explosion. It can give exposure, contamination for toxic gas and whatnot. Okay, fine. So that is why I think if you have like gas, natural gas, being transported from one station to another station, it is important to monitor the pressure of the gas so that it is not leaking or what. So if there's a leaking, you will see that the pressure become reduced. Then this can actually indicate that there's a leakage somewhere, and I think immediately that area need to be evacuated. Okay. Basically, we have 5 major techniques for corrosion control. This actually you need to remember, but I think later on we will study this in detail. The techniques for corrosion control. We have the first one, material selection. This is actually important if you are considering to produce alloy. Okay. So what does it mean by alloy? Alloy actually means that a metal, okay, that is produced by combining okay, 2 or more elements. Okay, if it is like stainless steel, SS, so you have like SS306, you have SS316, SS318. Okay, so all these are actually having different compositions. So you have iron, you have a chromium, you have like manganese, you have what? Other thing, molybdenum. Okay, so all these are actually giving a different percentage. Okay. So you know that all these materials is actually, especially chromium, is known as the corrosion resistant element. Okay, due to the fact that chromium can form passive layer. Okay, so that is why you will see that for stainless steel, even though it is made from steel, you cannot see that stainless steel corroded. It will corrode unless if you damage the passive layer. Okay, like for example, if you take a knife made from stainless steel, you see that it's not even corroded, but when you scratch the surface, you make a deep cut, a deep scratch on the surface, what will happen is you will see the material or the stainless steel will corrode, especially at the region where you make the scratch. Second methods for corrosion control is by controlling the environment. So we have talked about the environment on the presence of oxygen and also the presence of water. Okay, many things, maybe other considerations like anions or others. So if you control the environment, like for example, if you control the humidity of your environment, which actually can lower down the content of water, and this is also one of the good reasons, okay, to control via the use of dehumidifier. Another thing is if you want to control oxygen, you can use what? You can use oxygen scavenger. Okay, oxygen scavengers, for example, like hydrazine N2H4. Okay, so these examples of oxygen scavenger where the oxygen scavenger will react with oxygen to produce nitrogen gas with water. Okay, so no more oxygen. So when there's oxygen, so you know that oxidation process can occur. When there's an oxidation process, then of course corrosion process can occur. Another thing is by isolating the metals and alloys, okay, by creating a barrier. So this actually by means of protective coatings using paints, okay, and also you have like the fourth techniques, electrochemical protection or induced current techniques. Okay. So induced current techniques for electrochemical protection, you can have two. You can have either cathodic protection and also anodic protection. Cathodic protection and anodic. So cathodic protection, what does it mean? It means that the metal to be protected will become cathode. Okay? And for anodic protection, the metal to be protected will become anode. We are going to learn this more detail in the next few subtopics. And finally, the corrosion control can be done by choosing a proper design. Okay, so this is more or less to reduce erosion. Because if you have a poor design, then you know that, okay, like for example, if you have an L shape like this, okay, so when you have a moving fluid, then you know that this will create cyclone and then this area can be eroded. So when it becomes eroded, then this surface is more exposed, then corrosion can easily happen. Right. So finally, the significance of corrosion control, of course, we have to consider, I mean, due to the fact of the economic factors, safety, and environmental concern. This is basically the comparison of annual corrosion costs in the US and also in Japan. Okay, the data is actually obtained from NACE, National Association of Corrosion Engineers. Okay, so what happened over here, you will see that In some techniques, it requires higher consumption for costing. For example, coatings. Okay. Coatings is one of the most widely used techniques for corrosion control as compared to inhibitors, cathode protection, non-metallic materials, and CRE, okay, the corrosion resistance technique. Is there any questions so far before I proceed to the other parts? Any question? Anything?
Doktor,
Yeah.
saya ada soalan.
Yeah.
Tadi doktor dah cakap tentang mengenai humidity kan? What about temperature? Does temperature play as a factor for corrosion to occur?
Okay, basically, yes. We have not come into the part where we discuss about the thermodynamics or the kinetic process of corrosion. But the answer will be yes, because if you notice, when you increase the temperature, okay, of course, the rate of reaction will become higher. This is actually due to the fact that the molecules or the particles will absorb energy, okay, externally from the temperature, and then will become more aggressive, and it will be vibrate more, and then will collide with another particles more. So the conversion of reactant to product, okay, from metals to metal oxide will become faster as you increase the temperature. So of course, temperature could be one of the important factors to be controlled in this case. Okay, any other question?
Okay, thank you.
All right, so we are moving on to the next part, the corrosion process. All the while we have, I think, being explained about the definition of corrosion, what will be the implication of corrosion due to the cause, and what will be this technique that we can propose to control corrosion. So we are going to study more details about how corrosion process can occur. Corrosion process can occur either by wet condition or dry condition. So that is why we can call this as dry corrosion or wet corrosion. So what does it mean by dry corrosion? Dry corrosion means that the corrosion process actually happens with the presence of gas. Okay? Presence of gas, probably moisture and water is not really the case. Maybe just a slight amount of moisture, because you can see any materials, metal materials around you that, for example, leather or some barricade that is made from metals. It is not been dipped in water or what. It's just exposed there naturally, but corrosion is still like produced. It is actually due to the fact that the exposure to gas, like for example, oxygen gas or other types of active gas that can actually triggers corrosion. Generally, metals or gas or metal vapors reaction involving non-metals such as oxygen, halogens, hydrogen sulfide. This one sometimes you can call it as H2S. It's very corrosive gas. Sulfur vapor and etc. Corrosion of a metal that takes place in the absence of conducting aqueous medium and occurs when there is no water or moisture to aid the corrosion, and the metal reacts with the atmospheric gas alone. As a result, when the clean surface of metal are exposed to dry air or other gases to form oxides, okay, or the other compounds on the surface of the metals. So this is part of example. You have silver reacted with sulfur dioxide to form silver sulfide, okay? And then when you have copper reacted with oxygen, it can form copper oxide. Wet corrosion, in return, as I said, when you have the exposure of water with relative humidity exceeding 60%. This is actually related with the environment near to the, to the sea, like marine, anything that is near to the water source, marine, river, whatsoever. Wet corrosion is an electrochemical phenomenon. Why does it call electrochemical? Because when you have wet, when you have like water, this means that you have electrolyte. And then your metals will function as electrode. So this actually the interrelation between metals to electrolyte. So that is why it is called as electrochemical phenomenon. When the two metals are contact in water containing salts and electric potential is formed between the two different metals or the surface of the same metals with different surface condition, this causes the dissolution of a less noble metal. The more noble metals remain protected, but the less noble metals will corrode. And finally, the wet corrosion is most efficient in waters containing salts such as NaCl. So that is why you will notice that in marine or in the sea, normally corrosion process will become more aggressive because you have salts or you have like this one, chloride ion, which is known to be aggressive. Anyone knows what will be the concentration, equivalent concentrations of NaCl in the seawater? Someone knows? Shamira, you have any idea? Not sure. Shamira?
Yeah, I'm here, Doctor.
Okay, so NaCl in a brine solution or in the sea normally around 3.5 to 5%. This is actually a weight percent, weight over volume. Okay, so the concentration is quite high basically. So that is why you notice that anything or any metal structures exposed in the marine environment will experience severe corrosion as compared to in the normal condition. Okay, this is actually due to the fact that this salt is actually highly conducting solution, and chloride may also increase the corrosion rate of the metals. As I said, chloride ions is known as to be aggressive anions. It can actually trigger the attack, and when you have an aggressive attack on the surface, what happens is the corrosion process will become faster. The most metal occurs via electrochemical reaction at the interface between metal and electrolyte solution. And when we talk about corrosion, we cannot run away with electrochemical reaction and also redox process. So remember why corrosion is known as redox process, because it involves oxidation and also reduction. So imagine that when you have a metal dip in the solution, okay, for example, like this one is Fe, okay, you have probably like acid solution, HCl. What you will notice is that you will notice this metal will start to have a mass loss. It will be attacked, and then you will also see that there's formation of bubbles. This actually indicates something. The first indication is that, okay, you have an oxidation process. The oxidation process is basically known to be metal dissolution process. So what will be the half equation? Okay, so when you have metals, like for example this one, iron, Fe will become Fe2 plus 2 electron. This is actually the oxidation process, because oxidation process is normally related with the formation of electrons. Okay, remember, I mean, those who are not from chemistry, maybe you have to know that oxidation means that formation of ions plus with the formation of electrons, right? And the next one is basically known as a reduction process. Okay, so since in the electrolyte you have aqueous acid, so part of the ions that will be present in your electrolyte will be H plus. Okay, what else? OH minus if it is aqueous or water, plus with Cl minus. Okay, in this case, I think the example that I give you is basically an acidic solution. So you have H plus more dominant, because as I said in the first two chapters, when you have a more concentration or high concentration or high activity of one species in the electrolyte, this will actually reflect to your potential or your overall cell potential. Okay, so that is why I think between OH minus and H plus, this is more, I think, priority, to be considered for reduction because of it has high concentration. I'm talking about in the case of acidic. So in acidic condition, okay, you will have a reduction process of 2H plus 2 electrons producing H2. This is actually the hydrogen gas. The 2 electrons produced from the oxidation process will later on will be consumed by the other terminals, okay, for the production of hydrogen gas. This actually related with hydrogen gas evolution in acidic condition. But if it is not in the acidic condition, imagine that if this one is just a normal water, then your reduction process will be what? The formation of hydroxide ions. So you have like water, okay, plus with oxygen plus with water, H2O, okay, plus with electrons. Maybe this one, if you balance it out, okay, you have electrons, then it will form OH minus. Okay, so maybe I can just like write it here. You have like 2, then here you can have like 4, okay, and this one you can have 4 OH minus. This actually in the case of if it is in neutral, okay, condition. So in a neutral condition, it is normally the formation of hydroxide ions, hydroxide ion formation. Right. So later on, when you have Fe2 plus produced and OH minus produced, this will be reacted together, okay, to form the first product of corrosion, ferrous hydroxide. Okay, so this ferrous hydroxide is known as green rust. The first corrosion product. Okay, and forgot to tell you that during the process, oxidation and reduction, this actually occurs in a specific terminality, where for oxidation it is normally occurs at anode, and then for reduction it normally occurs at cathode. Okay, the other types will be like, I mean, after it has produced like green rust or ferrous, because this is Fe2, so ferrous hydroxide, it can easily further oxidize, meaning that further oxidation process can occur. It can form another stable product known as brown rust, okay, ferric oxide, ferric hydroxide. Okay, all right. So basically, I think this slides literally tells what I have explained earlier. The reason why it is known as redox reaction because it involves oxidation and reduction. So a loss of electrons, this is actually a loss of electrons, and formation of electrons is known as oxidation, while the gain of electron is known as reduction. This is actually you gain or you accept the electrons. Okay. All right. So as I said, the electrons produce actually created terminality. So you have anode. Anode is the electrode with anodic or oxidation reaction is occurring. Meanwhile, cathode, it means that the electrode on the cathodic or reduction reaction is occurring. Okay, so you can have like this one. I mean, like galvanic cell. This is actually a galvanic cell. Galvanic cell means that you have like two metals connected together. So when you have two electrodes connected together, then which one will be anode, which one will be cathode, depends on electrochemical series. Electrochemical series determine the terminality. Okay, between zinc and copper. You know that zinc, okay, the standard potential is around minus 0.7 volts, and then for copper, the standard potential is around positive 0.2. Which one will be anode? Which one will be cathode? Of course, this one will be anode. Reason why zinc will be anode is because the value of standard potential is more negative. So when you have a more negative potential, then this mentioning that the metal is more reactive. And when it's become more reactive, this actually eventually tells you that it can easily oxidize, and this actually will form anode. Meanwhile, for this one, you will notice that the standard potential is more positive. Okay? More positive, okay, potential. Then this can be notified as less reactive metal. Then when you have a less reactive metal, then this will actually undergo reduction and can be noted as cathode. Any questions so far from the floor? Anything that you want to ask or you are not understand? Nazira, okay ke?
Okay.
Okay, all right. Again, this one is actually just a recap how you can calculate the overall cell potential. Okay, we have learned this in chapter 1. How we can actually calculate the overall cell potential is basically by looking at the reduction or the cathode potential minus with anodic or oxidized potential. In this case, I think I've told you that for zinc, the standard potential over here is given minus 0.76 volt. And then for copper, it's not 0.2, positive 0.34 volt. Okay, then you know that this will be anode, this will be cathode. The overall cell potential formula is E naught cell is equals to E naught cathode minus E naught anode. So we just substitute the value 0.34 minus with minus 0.76, then you will get the answer positive 1.1 volt. This is actually the overall cell potential that you obtain. Okay? The initial potential created over here is positive 0.34, and this one over here, E naught is equals to minus 0.76 volt. Okay? Similar things to show the examples, which one will be anode and which one will be cathode. Right? Similar things as well. I think just to show you the reactivity between the two. You will see that over here, okay, for iron, the cell potential is basically minus 0.4 volt. Just now for copper, positive 0.3 volt. And you have another pairing, which is iron with zinc. Iron still the same, minus 0.4 volt. And for zinc, oops. Standard potential for zinc is equals to minus 0.7 volt. So for this type of pairing, when you have iron to copper, okay, you see that this is more reactive as compared to this one. Then this will be anode. This will be cathode. Between iron and zinc, you have like minus 0.4 and minus 0.7. This is more reactive, more negative as compared to iron. Then this will be anode. This will be cathode. Let's look at the arrow. You will see that the electron movement, okay, is basically from anode to cathode. Anyone knows why it is moving from anode, not from cathode to anode? What's the reason?
Because anode,
Yeah.
because
anode is what?
Because anode is oxidation, so it lost electrons, so the electron will be supplied to the cathode.
Okay, so who is this? Syamira ke?
Mariam.
Oh, Mariam. Oh, Mariam. Wow, dengar suara Mariam. Okay. Right. Yes, correct. Because if you notice the half equation, as I mentioned earlier, okay, you'll see that over here you have like iron produced. Iron, sorry, Fe become Fe2 plus 2 electrons. So these 2 electrons actually produced during oxidation and later will be transferred, okay, into cathode. Okay. So that is why over here you will see the electron movement from one terminal, which is from anode to cathode. From anode to cathode. I hope it's clear for you guys. And we also have gone through standard, hydrogen electrode or standard electrode potential. This is actually to indicate that every materials or every metal have its own standard value. So this standard value is measured using standard hydrogen electrodes. Reason why is because standard hydrogen electrodes like this one, it is actually producing 0 voltage. So you can use this as a reference. Okay, when you use this as a reference, you know that it will be always 0. Then the potential value that produced, okay, is actually the potential value for the studied metals that you put. Again, the electrochemical series is not something new. We have also seen this in chapter 1. Okay. But what I want to emphasize over here is that you have understand that for the more negative, okay, potential, this is actually indicating that you have a more reactive metals. When it goes down, more negative, more reactive metals. Then you have more anodic possibility as compared to the positive potential. Okay, so for more positive potential, less reactive. Okay, so when you have a less reactive metals, then it can be more cathodic. All right. So again, the same thing. I mean, on the standard electrode potential or standard electrochemical potential, you'll notice that all electrode reaction is written as in the reduced form. So you can actually see the potential values noted over there. Okay. Meanwhile, for alloys, alloys also have its own special electrochemical series. This is actually just to tell you that when you produce an alloy, it depends on the composition of the element, which will determine what will be the reactivity of the alloys. So you can see over there, like graphite. I mean, graphite is just like carbon only. It's non-conducting materials. Okay, then yeah, this one will become like more noble. So that's why you will notice why graphite, platinum, titanium, and stainless steel is normally used as reference electrode in any electrochemical measurement. Okay, reason is because this electrode is non-reactive metal. Okay, so when you have a non-reactive metals, the potential that is produced, I hope you still remember in electrochemical cell, you have working electrodes, you have reference electrode, and also you have counter electrodes. You still remember what's the function of each individual electrodes? Maybe I can just test those who came. Hamda, you still remember? What's the function of, what does it mean by working electrodes? Still remember, Hamda?
Electrode that interest.
Yeah, it's a metal of interest. So meaning that if you put iron over here, then you actually want to study the behavior of iron. Reference electrode. Jihad, what's the function of reference electrode?
Reference electrode, metal or electrode be reference and should be non-reactive or no, that's not. I like standard calomel electrode or standard hydrogen electrode, silver chloride. Electrode that known the potential volume or the potential electronic potential pressure. Sorry.
Okay.
To measure the another potential pressure for the another electrode.
Okay, that's very well answered question. Okay, reference electrode actually is an electrode that used to measure potential. Because you know, when you put working electrodes, okay, the active metals into the electrolyte, this working electrode will produce potential and also current. So when it produces potential and current, you need some other electrodes to measure it. So reference electrode, okay, as I said, is going to be used to measure potential. And counter electrode is used to measure current. Okay, so reference electrode should be like I think, for example, you gave us the example would be like standard calomel electrode, saturated calomel electrodes, standard hydrogen electrodes. What else? Maybe like silver chloride, okay, and others. Meanwhile, for counter electrode, since it is actually to measure the current, then the types of electrode must be inert. Okay, sorry. Then sometimes you will see that this graphite, platinum, titanium, stainless steel can be used a lot in counter electrodes, as a counter electrodes. Okay, all right. So this is more or less of what I have mentioned earlier. Okay, the electrochemical corrosion reaction, you have like metals dissolution at the anode terminality, and then at the cathode reaction, you have, if it is in acidic solution, the formation of hydrogen gas. If it is in the neutral solution, then it will be the formation of hydroxide ions. Okay, so I'm going to skip this one because we have like gone through it in the initial stage. Okay, so it's just to show you how the rust is start to form. Imagine that when you have like metals or iron in water, so we already know that Fe will become Fe2+. This is the anodic reaction. And then in water, you have like oxygen also that later on forms the hydroxide ion. So the Fe2 plus reacted with OH minus, okay, hydroxide ion to form the first product, which is known as ferrous hydroxide. Okay, so this ferrous hydroxide sometimes is known as green rust. And ferrous hydroxide can easily oxidize to form a more stable product known as ferric hydroxides. Okay, FeOH3. If you have like OH, this one you know hydroxides. Okay, and depending on the concentration of oxygen, the pH, the amount of water, it can form another types of rust. It can form either ferric oxides, hydrated ferric oxides. It can form the magnetite, which is having this formula Fe3O4 and others. Okay, so things that we have to consider in corrosion electrochemical cell is that the establishment of anode, establishment of cathode, the conducting environment, which is in this case electrolyte, and the connection. You must have a connection between the two electrodes or the two terminality. Okay, so I believe this one is also part of the things that we have go through. Okay, just to show you if the material, if the corrosion happens in one electrode. So you will see that in one electrode you have one terminality on anode, which near to the water droplets, and the other terminal which is actually at the outer droplets, because this is where the rust formation forms, the rust deposits form, right? Okay, so this is actually to show you, okay, the corrosion reaction of iron. Initially, we know that iron, okay, can react with oxygen and water to form the first product, which is known as ferrous hydroxide. Okay. Maybe I can write this as green rust. So the green rust or the ferrous hydroxide can further oxidize to form reddish brown rust. Okay. Or this one we call it as ferric hydroxide. And as I said, depending on the amount of oxygen concentration, pH, water, okay, it will actually form different phase of rust. So we have one over here, we call it as oxyhydroxide. Right? Sorry. Okay, oxyhydroxides. This one over here is more or less on hydroxides, rust, and this one is oxyhydroxides, because you will see OOH, and it has different crystallinity. Okay, different crystallinity means that it has different crystal structure. Okay, you have alpha, beta, delta, and gamma. So alpha, FeOOH, is normally known as geotide. G-O-E-T-H-I-T-E, geotide. Okay, beta, okay, this one is lepidocroside. Lepidocroside. Okay, delta, FeOOH, is known as peroxide. Okay, peroxide. Okay, and then you can also have like gamma. Oh, sorry. Sorry. Beta is not lepidocroside. This one is actually acaganine. Beta. Acaganine. Okay, gamma is actually lepidopteroxide. Okay, and this one actually we have seen earlier. This Fe3O4 is known as magnetite. Magnetite. Okay. Fe2O3, this is a ferric oxide. Ferric oxide, and this is hydrated ferric oxide. Why is it hydrated? Because it contains water. Okay. All right. And the development of phase rust is actually stage by stage. You will see over here, the pure metals, when they start to oxidize, this is actually a layer of the first product, ferrous hydroxide. Further oxidation, further hydrolysis will form another products, okay, oxyhydroxides in the middle, and then another product forms like magnetite. Magnetite normally black in color, okay, will form in the deeper region. So you have like layers. So if you actually scrap off rust, okay, from a metals, how can you tell whether that one is actually which type of rust phase that you can know using what types of instrument? Anyone knows? How do we know the rust phase from the rust scraped off from the metals? Can someone knows? Can someone guess what techniques that we use? Atira mungkin postgraduate student, maybe no. Any idea?
Saya lupa lah. Dah lama waktu degree dulu belajar.
Okay, it's okay. Any idea, Shamira? You know? I mean, like, how do we determine the rust phase? Because all the while I'm talking about different crystallinity. I think I already give the clue.
Is it XRD, Doctor?
Yeah, correct. Okay, so the methods that we will use to determine which type of rust, okay, which phase, okay, for a rust product, normally we will use XRD. XRD. This is actually known as X-ray diffraction.
Doctor, how do we check with SRD?
Okay. With XRD, normally, as I said, when you have like take the rust and the rust powder or the rust, okay, you actually make it into pellet and whatnot, and then you run it using XRD. So the XRD results, it will give like a defectogram, okay, not good, but in drawings, but you will see that it will give a response, okay, like 2 theta with this one 2 theta, and this is the arbitrary unit, ABU, okay. So what you notice over there is that probably it forms a different peaks. So the peaks is actually related with the crystal lattice and whatnot. So every crystal have its own crystal lattice at specific 2 theta value. Okay, so that is why I think if you conducted XRD for rust, you will notice that it will be a mixture of different types of rust phase. So you know that maybe over here like around 10 degree, 30 degree, this is actually related with what? With geotype, for example. Then you know, okay, G, and then this one may be M, and then L. Okay, so this is actually the way how we indicate. And most of the XRD equipped with a library, meaning that they have already a standard of geotype. So like geotype, the 2 theta will appear at specific values, akaganite specific values, peroxide and lepidopteroxide. If the XRD doesn't have a library, then what you can do is you can run the standard XRD for each compound. If you have the standard, later on you compare. So basically, for those who are doing corrosion, you will do XRD. You just to check what will be the rust formation or transformation that forms. So you can have an idea when you do a modification or when you do a treatment, which one will form, which one will not form. Okay. Any questions so far? I think the names is not something that you have to remember. I mean, just for your information. Okay, so I guess probably the last few slides before we call for the day is just to see the reaction feasibility of corrosion. Of course, the corrosion process is related with thermodynamic laws. Okay. Of course, the type of law, the thermodynamic law that you can understand is energy can neither be created or destroyed. So the rules is that all spontaneous changes occur with the release of free energy from the system to the surrounding at constant temperature and pressure. Okay, so points to note is that corrosion is a spontaneous process. So spontaneous process, I guess I have told you earlier, delta T should be what? Spontaneous.
Less than 0.
Negative.
Oh, negative.
Okay. Right. So when you have delta G is negative, this means that the process is spontaneous. What does it mean by spontaneous? When you put the material, it will automatically or will immediately, okay, form product. Immediate, okay, product formation. Okay, and each process actually release the free energy. This is actually the free energy, delta G. If you look on the energy diagram from reactant to product, so this is actually the one that we look into. This is reactant, this is the product. All right. So the energy needed to form a product or to overcome the energy is known as activation energy. This is actually activation energy, EA. Okay, the energy, okay, that is needed to form the product or the free energy release is known as delta G. This is actually the delta G. Okay, all right. So free energy is released in the process. Metal will return to its stable state. The driving force for corrosion reaction is actually chemical energy. Energy stored in the chemicals, and free energy actually means by the portion of internal energy available for causes corrosion reaction. All right. So there's a few things that you need to consider that may reflect to corrosion process. The first one is known as defects in the metal structures. When you have the defects in metal structures, then corrosion process can actually occurs easily. The first one is actually known by point defects. Okay, so this type of defect is basically well known because it has imperfection in the lattice structure. Okay, point defects normally occurs when you have alloys. Why I think point defects normally occurs for alloys? This is actually due to the fact that when you introduce another element in the lattice, okay, it can be either interstitial or substitutional. Okay, I guess maybe if you learn materials chemistry, because I'm teaching materials chemistry for undergraduate, we have this term, Frankl and Skosky effect. Frankl and Skosky effect actually deals with the vacancy and also the interstitial formation when you add impurities. So we actually said that when you produce alloy, you actually add impurities. For example, like carbon steel. Okay, carbon steel FeC. You have iron and carbon. So carbon is being added as the impurity or something that you add on to the iron so that it will become more durable, more mechanically durable. Okay. But when you introduce carbon, what happens is that it can be introduced substitutional, means that it will substitute the particulates. Okay. When it substitutes, sometimes there's a vacancy forming. And if the structure is small, then it will be, forming in between the lattice. This actually means by interstitial, right? Vacancy means a missing atoms, and substitutional actually defects of a foreign atom. Interstitial defects is actually the atoms will be squeezed into the structure. So when you have a vacancy, then you know that this region will be too weak. Then oxygen and water can easily goes into this region, which is vacant, then can easily react or damage this structure. Okay. Right. Another type of defect is known as line defects. Okay. This more or less the plane of atom is not perfect. We are talking about the crystal structure of rust, the crystal structure of a metal. Then, if you have a defect, for example, the lines of the plane is not aligned together, then what happens is still it can create gaps, and then oxygen and water can penetrate and can damage this region. That is why, if you notice, if your car involved in accident and you have a scratch, okay, so you see that the scratch region, theoretically, you have some defects on the crystal metal structure. Then this will eventually result in a corrosion. Okay? You will see the car that have been scratched, immediately within few hours, the line of the scratch, you will see that it become corroded. Okay. Volume defects is also another things. Okay. The formation of void, the cracks that are introduced during the process of inclusion of particles of foreign matter embedded, and you can also have a surface defects. Okay, where surface defect normally occurs if you have non-flat surface, non-homogenized surface, and whatnot. So that is why anything that you want to do with, corrosion measurement later on, you need to polish this, the surface so that it will be homogenized. Other thing will be the heterogeneity in metals due to the atomic, microscopic, and macroscopic reason. This is actually due to the grain boundaries. Grain boundaries always happens when you have alloys, because grain boundaries actually forms when you have a separation of different phase, alpha, beta, or whatsoever. Okay, so I think for the thermodynamic aspect for corrosion reaction, we will continue next week in the next class. Okay, but before that, is there any question so far? Anything that you want to ask? And forgot to tell you guys that today we are going to have quiz. I will post the quiz today, and I will set the deadline until 10 p.m. because I think some of you working and not having time to do until 5. So I just extend the time a bit until 10 p.m. so that you have time to do it. So I will share the quiz later on in your e-learning. So please check. And I think assignments, if you do have question or assignments, you are free to ask again. But is there anything that you want to ask about the lecture today and other things? Anything? Hamda, is everything clear for you? Okay. Yeah, but Jihad, it's okay for you, Jihad, Mahdi?
Yes, yes, doctor. Thanks.
That's okay, Doctor.
Right. So I believe if there's no further question, then I will call for the day today. So it's okay. The recordings I will post later on in the YouTube. So of course, if you have any problems, just text me and we'll try to solve your problems. Once again, thank you very much for your kind attention for today's lecture. I know it has been long for you guys, but thank you very much for your kind attention and hopefully to see you next week on Tuesday. Thank you. Assalamualaikum and have a
Thank you
good
so much,
weekend.
Doctor.
Yeah.
Thank you, Doctor.
Thank you, Doctor.
You're welcome.
Thank you, doctor. Bye-bye.
Thank you, Doctor.
You're welcome.
Thank you, Doctor.
You're welcome.